All right, so let's get started.
I have one question. So, do
Yes.
you need, are you going to write the reports or the student going to write the reports?
Yes, I think I wrote in the sheets that I posted that each of you are expected to write, or maybe in the email, about 5 to 10 pages of report. Okay, the point is not the amount. I told you already, right? And then the point is not grab something and then try to write up that. That's also fine. But just try to understand, do some exercise, and let me know what you have understood. Okay? And what you think is the essence of the topic. So that's that. Okay, are there any questions? Okay, if not, let's jump in. So we will start talking about path integral this week, and from next week we will start renormalization. Okay, so last time I finished the lecture by saying, let me finish writing path integral. So far we have done quantum field theory with the technique of canonical quantization, right? And then I sort of fill out the entire board. What was the program all about, right? So now we will talk about the path integral. First, we're going to derive the path integral, which probably you have seen it before already. Path integral theory in the quantum mechanics. There, the question I'm asking is that if I prepare a state at time ti, which is the state localized at t xi, and then I evolve over time. Then I ask, what is the probability of that evolved state overlaps with the state that is localized at xm? And then we will derive that this looks like this. Did I want to write action? Sure. Okay. And then using this, so we're going to basically derive this, build up most of the intuition from this. Then we're going to basically derive a quantum field theory version of it. So QFT version of it. And then there, instead of asking, more general state, we're going to ask a vacuum to vacuum transition. So I will ask vacuum at t equal to ti. And then I ask, what is the probability of that it ends with a vacuum at tf? And then we will show that this takes this form. We will discuss the meaning of all these expressions. And then once we get to that point, we will start talking about a lot of aspects of path integral and asking more physics questions. Okay, so that's what I want to discuss today. Good. So let's talk about first quantum mechanics case. So once again, we want to ask that question. So basically, there's a time interval from ti and tf. So we can imagine two different situations. One where Hamiltonian is time independent. Okay, so then this expression is actually correct expression, right? So time evolution is controlled by time independent Hamiltonian. This is the correct unitary time evolution operator. The second case where Hamiltonian is actually time dependent, then this particular expression obviously is not well defined, right? You know that you have to do more time ordered version of time evolution. So either way, either h is t independent or time dependent. So even if h is time dependent, we can imagine that there's a small interval called delta t, where h is roughly time independent. Okay, or you can just imagine that h is time independent, and then I'm gonna do anyway this exercise. Either way is fine. So I'm going to basically slice out the time in n+1 slice. So t1 to the t10 is inserted in the middle. Okay, and then so here there is a completeness relation for x solid state I'm going to use. So I'm doing 1 plus 1, 0 plus 1. Is 0 plus 1 quantum mechanics? Yes. Okay, so I'm doing the one-dimensional one-time theory. That's what I'm saying. So let's start working out this expression. So here is I start. Then once again, I'm gonna insert entire set of this identity. So let me start from here. Okay, so just so that I save some chalk, let me just write a delta t. Is this? Okay, this entire thing is delta t. And then I'm going to rewrite this in terms of let me see. Yeah, let me just write here. It's going to be big expression. So dx1 and dxn. So each of the slides, I'm inserting identity. And then there's xn that I will have minus it delta t. So let me write as if Hamiltonian is time independent, but if it does have a time dependence, you can just insert Hamiltonian evaluated the t at the last slice. Xn, you keep going until when? Well, until x1, and then so I'm here now. I'm evaluating time delta t x I. Once again, if Hamiltonian is time dependent, and then you're actually doing very small interval evolution where on that scale where h is roughly constant. Okay, so this I just did it so far, nothing new. So generically, you see that you have a whole bunch of vectors that looks like this. There's some Hamiltonian sandwiched between two axes, in neighboring two axes. So let's just evaluate that thing. So here we're going to just evaluate x of j plus I e to the minus h d j. Okay. So and then here let's actually rewrite Hamiltonian as e to the minus. So Hamiltonian has two pieces. One is, let's consider non-relativistic quantum mechanics, the potential part, which is x. If Hamiltonian had a time dependence, it will have a time dependence. But again, we can just do the exercise assuming Hamiltonian is time independent. That's fine for now. So then this is easy to take care of because now remember this is an operator. So this is an operator that I'm doing the quantum mechanical. If you want, just to emphasize that Hamiltonian is operator, I just put that here. But this expression I'm not going to fix it. So this is easy to take care of because if potentially is a function of x operator, then we can just work it out. Minus the xj. So now this is just a classical function. Okay, so now we have to take care of this. And since it is momentum operator, obviously you want to see momentum against state rather than position against state. So what did you do? We're going to insert. So let's continue here. We're going to insert another complex relation for momenta, which I can write it as p2 and then there was this. Oh, I forget delta t. Sorry, delta t. That multiplies everywhere. Good, and then here too, delta t. Good. So I have a v of xj delta t, and then xj plus 1. You can put anywhere you want. So t, j, e, j, and then e to the minus I operator. And then x j. Good. So that's better. So we get what we get. So we get dt over 2 pi e to the minus I d xj delta t. Let's combine. And then this one give you delta t. Let me separate out because. Sorry, let me separate out because they will turn out to be useful thing to do. So this is nothing to do with the momentum, right? This part has nothing to do with the momentum. Let me just pull out of the integration. That's what I mean. This will give you e to the minus p xj delta t. And then there is momentum integral. So first of all, now this is very easy to evaluate. So you already get it. So minus ipj squared over 2n delta t. So now this is just number rather than the operator. And then you have this sandwich of two. Okay. Now you have seen that this is given by e to the minus ip j dot xj. Now, one thing that I want to emphasize here is that yes, you have seen this. Perhaps with a 1 over square root 2 pi h bar. It's pretty there in quantum mechanics. And one thing that I want to emphasize is that this is true. Okay, this is true for any conjugate state or operator x and p. Okay, so this particular relation, if you like, this appears in the Fourier transform. Okay, what is Fourier transform does for you? Well, it goes from x to the p space. What does that mean? It goes from the one space to its conjugate variable space. Okay, so that's what this happens, right? Or you can show explicitly that this particular form is always true whenever you have a two operator here, x and p, which are conjugate variable in this sense, in the quantized sense. Okay, so this will be used important in the quantum field theory case which we will study. So for any two operator quantum field, it's a conjugate momentum operator, which satisfy this with a delta function here. Once again, they will satisfy this. So I'm just saying that for now. So let's continue. Then we arrive at a point where I have this gigantic integration, but let's write it out. E to the minus 1 over 2. Let me just write in a suggestive form. Delta t over m I p j squared. So that's the first piece. The second piece has what? Minus plus I x j plus 1 minus xj p. Okay. Done. So now I just need to do this integration, which you can do. So that integration is just the Gaussian integral. So let me just recall a couple of Gaussian integral formula for you. So if you had, since I'm doing the p integral, let me just write p e to the minus over a p squared, for instance, then this is 2 pi over a. Okay, or perhaps you have seen this pi over a, right? That's done. Because of this, there are a couple of things you can do further. So first of all, if p minus to the equals infinity, p to the other power with this Gaussian vector is always 0, simply because this is even, this is odd. And an integral with p to the even is all solved. Okay, very good. What do you mean by that? Well, just demonstrate. So for instance, EP, let me graph e to the minus EP squared. So suppose I do the derivative with respect to A or half A, right? Treating the entire grid sector. So you get EP P squared, I promised, A P squared. But you know this formula. On the other hand, this is 2 pi over A. So you know how to take the derivative of this formula. So therefore, you know how to compute this type of integral any given power by just taking extra more derivatives. So that's doable. That's what I mean. Everything is doable. The last big identity, or maybe not the last, but you have to generalize. So let's, instead of this factor, let's also add a linear term. So hopefully you see what I'm doing here, right? So here we have to do the Gaussian integral. And for us, this is my A, and this entire factor is my J, right? That's what I want to do. And complete the square, I guess. So this is what? dp e to the minus half p minus o j over a squared, and then I haven't finished it, by the way. That and what? J squared over 2a, right? Because you have to add this somewhere, right? Good. So
JP, not JP.
what's that?
Exponential JA, not JP.
That's what I meant. Thank you. Yes, exactly. Yeah, I was just checking. Okay, so since I'm doing the indefinite integral, I mean, this is a shift, it doesn't make any changes. So that's again the same factor. Therefore, this integral is 2 pi over a. It's the j squared over 2a. Good. Okay, so we know how to do it. And eventually we will have to generalize this to matrix. So suppose I have P1, Px into n-dimensional metric thing to a Pi ij bj plus ji bi. Yes.
Does it hold for arbitrary complex A?
Arbitrary complex A. So for real, this is just true. Complex A, I think so, because if you recall the derivation of this thing, I don't think it makes any assumption about the nature of A. Let me make sure.
A is negative.
A is negative. Oh, that's what you meant. Oh, but so if this is not convergent, how do I even think about this integral? Is that the question? I don't know who said that. Yeah.
There's some other related.
Yeah. Okay. So certainly convergence is important. Yes. Very good. So in other words, good. So okay, since you pressed me, so how do I do that? So let me call this integral to be I. Okay. Let me call this integral to be I. So then I squared is I have 2. So let me just write it as x and y. E to the minus. Can I just call a only? Forget the half. Then x squared plus y squared. Right? Okay. So then this is the integral of 2 plane, which I can write as a d by r dr. Good. And that is e to the minus 8r squared. So we can check when this fails, like when this integral will fail. This is 2 pi. And this I can write it as a half of the r squared, e to the 8r squared. So let me just call it a z. So that integral seems like easy to do. Now this integration is from the 0 to infinity. So obviously, now what kind of a is acceptable depends on when this integral is formed. Okay, so this integral is likely pi times, but then minus 1 over a e to the minus a z, where z runs from 0 to infinity. So yeah, so if this is random complex, obviously this is ill-defined. And this is a positive. Oh my god, right? This blows up. When this is a positive or real, this is well-defined. Then you see this is that. And this part is always well-defined. And so usual answer that we got here is when this is positive real, because this makes a 0 contribution and then you pick up the 1, that's way. That's how you get that. But yes, what is this? A. Right? So at least super naively, meaning as a physicist rather than a mathematician, it makes sense to me when A is a positive real. Yes. And when this is a complex, okay, let me know.
I think it is okay when real A is positive.
That's my guess, because if you look at the definition of gamma functions, but it's stuff like that, there's always a real part of something is greater than 0, it's well-defined.
Well,
Okay.
I think that's also true because if it is only true merely imaginary, then that power will be also negative, mostly.
Yeah,
then
that's also
it will not converge, but the real part is negative, then the oscillation will be suppressed by exponential. So
right.
so I think yeah, it is enough to state that the real part is positive in there.
Yeah, if this is pure imaginary, I know the answer too, because that's almost delta function. Right? Modulo minus infinity should be there too. So it's a half of delta function if you want. Okay, which is divergent, I believe. It's not a well-defined function. But anyway, so for now, let's stick to the fact that we're playing with a positive real. Okay? And then ask the question when we have to. Okay, so what I was trying to say, again, here. So, so in this case, what you can do, obviously, is that you can diagonalize this matrix. This is, so I'm assuming this is symmetric, real or complex transmission. Either way, I'm assuming the fact that this is a diagonalizable with a real eigenvalue. Okay? So in that case, what do? Well, you just rewrite this. You dagger A, U, oh, I don't want to put dagger there. P. So now this assumed to be a diagonal matrix T with a real eigenvalue along the diagonal. So then you have to rewrite this as what? Like U J dagger UP. Okay, so now this is my U variable. So everything should be written in terms of UP, which if I call to the Q, then integration turns into DQs. But obviously there's a Jacobian factor of whatever PQ, which is 1 if you can do this diagonalization of the orthogonal unitary way. So you see that this factorizes into separate integration, each of the eigenvalue parts, right? And so well, minus half Q diagonal Q, and then plus instead of a J, I just need to use this source here. This part. Other than that, everything is exactly the same. So one can even write this immediately. So if I think about n by n matrix, this is n, then this should be n vectors of this stuff. Then I can write it as 2 pi to the n, because I'm going to have n vectors of that. And then this will be product of all the eigenvalues, which is nothing but determinant of A matrix, and then I have this J. So that's, you see, J, what did I say? U dagger, UJ, if you want, if you really keep track of it. But in between, I will have 1 over A, which where is it? 1 over A, which is nothing but A inverse matrix, and then UJ over 2. At the end of the day, you can check that this is totally doable. Okay. So with that, let's come back to this quantum mechanics example. Finish the calculation. What if A is not invertible? What if A is not invertible? Where was the question from? You? Okay. You mean that non-invertible or non-diagonalizable? You really meant non-invertible?
I mean, determinant thing.
Good. So that happens. That happens in quantum mechanics. For instance, we already saw the example. So in when we talk about the U1 massless theory, we saw that part was had a massless zero eigenvalue. So it was not invertible. And then we fixed it by including gauge fixing and so on. So whenever we encounter that problem, we will have a fixing. Okay. So for gauge case, we have to add a gauge fixing term so that the entire thing becomes invertible. So we can do that. And then oftentimes we will encounter where this also has a zero mode, called a zero mode, because it has a zero eigenvalue. And then in the context of instantons and stuff like that, we always encounter that, and we know how to deal with the zero mode if you want. Okay, so, which is almost the entire point of studying all those subjects, meaning the day captures a lot of physics, and suddenly all comes from the zero. Otherwise, it is not very exciting important feedback. We just try. Another question before I come back. Yes.
I think I missed the point. Did you assume the Jacobian one?
Yeah. Okay. Yes. If not, you have to keep track of it. And sometimes you do have to keep track of it. Sometimes this will give you important thing, for instance, along the way. So for now, I just assume that. But here also, I can simplify, so let me do it. So like so, this, and then, oh, this, where did 0 come from? Who put this here? Oh, this is 0. So if you keep track of it, you get something like this divided by like product of two i's. You know? Okay, because you will have all factors of that. So this entire thing can be rewritten basically as e to the. Of course, you just cancel out this Jacobian, sorry, the unitary rotation factor, orthogonal factor, and this will just become j, a inverse j over 2. So this is completely captured in terms of metrics or me. All right, so we're naturally here. So let's finish this calculation. So what we have done, we have erased everything that we started so far. So we were asking quantum mechanics question that evolves from xi to xf through the time evolution with slice O. That was not the object, was it? No, this was not the object. So I erased a very important thing. This, I wanted to compute this factor, e to the minus I, H, Hamiltonian, H, J. So to do so, we inserted the complete set of a momentum eigenstate, J, okay, and then we need to finish this computation. So this now, after this discussion about the Gaussian integral, is literally just a simple Gaussian integral. So let's do it. Any issue? No? No. I mean, no, if you have a question, feel free to ask.
Okay, then I have a question.
Okay.
처음에 좀 적으실 때 JU 배거랑 UJ 사이에 A 인벌트가 들어가 있지 않았습니까?
So I wrote naively. So this is a more free expression. In other words, once you diagonalize this, it becomes the product of n separate integrals, right? So if you do it, basically you will end up with this expression. Then this part cancels out, and then I can rewrite the entire thing in a matrix form, which will look like this. So the final answer is that prefactor times this. That was what I was trying to say. Good. So I was a little bit sloppy. Okay, back to this point. You can certainly read off this integral after that formula. Let me just write the answer for you. Good. So this will look like. So this integral part will become some crazy prefactor, as always. If that has not been your physics so far, from this time on, you will already see crazy prefactor. Good news is you don't care about that eventually, but let's see. So then I'm going to write, so this is corresponding, that corresponds to this prefactor. I'm going to write down this exponential factor. So that will be xj plus 1 minus j over delta t squared t. Okay, good. So this prefactor I call n tilde. Crucially, this is time independent. You might say, what do you mean? This is time. So this is a time interval, but it is independent of which interval I am in. That's what I mean. Okay? This is time independent prefactor. Is that clear? Okay. And eventually crazy infinite prefactor. If you take delta t goes to infinity, 0 comes out. If you take delta t goes to 0, that's like 1. But we don't care. Because we're physicists. And we make it for purpose. Right? Okay. So then what do we get? So now if I combine everything, okay, I inserted a lot of i's, x's, and the p's, and then I will have a product of all these factors, which collapses to this. So if you collect all of that, you will get n tilde to the nth power, because there's n insertion of time slices. And then I still have this integration over the axis. And then integration over all p, I have done it. So if I collect all of that, I will get e to the I to start, delta t, nice. And then that thing. So x, like, what is it? X n minus x n over delta square minus v evaluated at the last point. And then you will have whole product of this thing, delta t, until last point. Yes,
There should be n over 2.
exactly. Good. Delta t, m over t. Okay? So if you look at this is nothing but Lagrangian, right? At, if you want, x and tn. Basically, therefore, since it's a product of it, this will be sum of the exponent. So this will become basically, so there's that factor. And then let me still write this. So this entire thing will look like, therefore, yes, I will write one more redundant expression and then I will finish up. So this is totally redundant, so I just rewrote again. Now, I'm going to write this as, first of all, let me call this prefactor to be just n, because I don't want to write a lot of things. Now, this is, I'm going to write it as this, and then therefore, this is the sum of entire pieces. I'm going to write it this. So then let's understand if I make sense, if I can make sense of this. So far, just equality. And then last moment, I did a little bit of a jump. So let's see if that makes sense to you. So what was this? Remember, I inserted the complete set slice by slice. So starting from xi, then I wanted to end with xf. And then each time slice, we inserted the x, this complete situation. Okay, each slice. And then what we said was that also this expression says you have the sum of all possible x1 values. For instance, this can jump into here, or this can be jump into anywhere else in this, right? That's what this integration does for you. Okay, and then you do all the same thing. So which I drew last time, you basically have the sum of all possible, possible path basically. So either you read this as a summing over that way, or you can just read this as a summing of all possible paths. So therefore, I just rewrote this into this form. And then this is literally sum if you want. This is like sum over L dt, which is not continuum version, nothing but this integral, which is the action. Okay, so that therefore, this quantum mechanical object can be understood as the sum of all possible paths weighted by the either I action. Okay, so that's the integral you've seen. And then, but we have the small one integral of one of proportionality factor, which is crazy, but we can do. It's very easy. Okay, good. So that's the quantum mechanics version.
I have one question.
Yes.
The picture you draw assumes that we have a time slice. That's fixed, but suppose we can change the time slice.
You mean it's change the
I
time?
mean like something like that.
Okay.
So then would it be still be okay there?
Okay, so the question was here assume certain time slice, or if you want to take the viewpoint of like four-dimensional geometry, and then I pick a particular foliation of space-time geometry with time slicing. I assume that's possible.
Yeah.
And then this emerges. If your question is whether there's a notion of foliation well-defined all the time geometry, GR sense,
So, I mean, that is independent of how we foliate the space.
oh, that was your question?
Yes.
Okay, so your question therefore is whether this final answer depends on the foliation.
Yes.
Here it doesn't matter in a sense because I'm taking Minkowski and quantum field theory, right? So within the context of Minkowski and quantum field theory, meaning there's a well-defined flat 3-dimension and then well-defined, like, clean time direction, I can always do. It's not like, I even gonna choose, but there's a well-defined time slice already prepared for us. So there's not even a question. And then if you want, this derivation was in that context. There's already clean, well-defined version of time slice, which I'm about. If your question, on the other hand, is in a more general quantum field theory, you possibly carve the space and time, possibly with the fluctuating quantum gravity. Okay.
Yeah.
So good. So I don't know sharp answer to the question. Even with the well-defined time foliation, people will complain, like, how do you make sense of this equation? I do make sense of this equation. Because I feel this way. Everything is totally fine. And on top of that, there can be that question, whether there's a subtlety regarding time foliation. Sometimes I guess it is important to understand all subtleties, which you always want to try, right? All possible subtleties, whether you can close up any loopholes or subtleties. Sometimes you want to move on and start making progress, because sometimes that itself can provide evidence for you. In fact, I think if I recall correctly, historically, in the context of the ramp shift in quantum electrodynamics, there was a big conference, people are presenting their radiated corrections to the lamp shift. And then people presented, right? There's a Dirac sitting, and then I forgot who. The original calculation was done in the more operator language, the canonical quantization language. Just the old operator ordering, and then contraction, blah, blah. It was done that. And then Feynman presented, let me present a different way of computing the same thing. He presented a path integral. And then, like, people asked, including Dirac, is it unitary? He said, okay, I don't know, but it works. Somebody asked, is it blah, blah? I don't know, it works. I don't know, he asked him, I don't know, it works. So, in the end, it works. And then we start understanding all these deep questions. Like, how do I see the unitary? How do I see this and that in this context? But beyond modern days, we understand way more than we could have done without the evidence. Yes.
Two questions. In that case, A is your imaginary, so
Oh, sure.
we
Yes.
have we done some analytic continuation?
Yes, good. So, good catch. Good God. This is also imaginary. Everything is crazy. Good. So let's make sense of this one. What do I mean by these expressions? That's the question. Great. Yeah, I guess at least this helps you with that helps. So at least in this case, I can make sense of this problem because I can do the analytic continuation. T goes to I times T. So basically I pass on to the Euclidean. In fact, it is Euclidean space that these are very well defined and everything understood. So then this is cleaned up integral. Okay, and then we can come back. There's this big question about the analytic continuation from the question was, so we live in, I don't know if you live in here. I'm in here temporarily. And then we can do the analytic continuation like so, then this is like t squared minus x squared minus y squared minus x squared. If you do the analytic continuation like so, then this turns into minus of t squared plus x squared plus y squared. So this is Euclidean now. That's now signature plus. And yes, I think that's how you can test it. Good. Yes.
I think with delta t is 0, then enter the rules of
Were you asking if a delta t goes to 0?
Yeah.
I have to do something?
I think if delta t goes to 0, then and field goes on.
Infinity, yes.
Then how do we define?
Exactly. That was the whole my speech. Doesn't make any sense. Right. It doesn't make any sense. And this is beautiful. Yeah. Okay. So yeah. So now I'm doing only the finite slicing, right? And then obviously we're talking about infinite slicing. And you will see now, which I will do QFT version of that. Not only there's a one version of the craziness into it, there's a continued version of craziness into that. And yet, I'm happy with it. We're going to use it. Yes. So if you're asking mathematically, how do we make sense of it? Physicists say, who cares? Mathematicians say, I'm not going to even talk about this. And we do make progress in part of it. So yes, I'm not claiming that I can make sense of this. No, I'm not claiming.
But one thing that though, what we want to calculate is that is obvious.
Yes.
And this must be finite value, I think.
Good.
But
This is not.
yeah.
Right. Good. At least I will answer that question. So this I should be able to answer, right? So I know I want to compute finite, well-defined physical quantity out of the crazy infinite stuff. But I have to show that nevertheless I should be able to get the finite, well-defined physical quantity. This I will show how we can do that. Yeah. But this on its own, I don't. All right. Good. Let's move on. Yes.
What if the T is not transferred to the quadratic function of P? Is that indicates the Hamiltonian goes to the Lagrange?
Good. So your question is, if I understood it correctly, so here I'm assuming p squared over 2n, but generically we can consider some other possibilities of kinetic term, or in general, if I consider a more general form of the Hamiltonian rather than this clean this thing, how do we understand path integral? That's your question. So why don't I answer that question after I finish QFT version? Because I will even have to mention about it. Okay. Good. So you guys are excited about path integral, I suppose. Good. All right, so after that, let's actually do QFT, which I'm not going to do step by step, but now we can basically grab the intuition from this particular exercise, and then we can do it. So for this, let me take a simple theory, which is free theory of scalar, real scalar. And possibly I can add some potential. So for now, let me even throw in possible potential. And in canonical conjugation, we have done all of this. In particular, remember we had the field operator x and then associated conjugate momentum, which is obviously defined by dot, as we talked about. And then this you have to impose canonical conjugation, canonical commutative relation like so. So they are conjugate to each other. Okay? So just like we had in quantum mechanics, oh, this is long list. So let me do it here. So in quantum mechanics versus quantum field theory. So in quantum mechanics, we had an operator, either x hat, p hat, and so on, which are conjugate to each other. So in quantum field theory, so we're going to have a quantum field operator. Let me put hat for a second to be totally clear that I'm talking about the operator, about x, and then we're going to have conjugate momentum, and then they satisfy this conjugation relation. In quantum mechanics, so that's number one. Quantum mechanics, t pi was an argument. On the other hand, the value of position x and associated momentum are eigenvalues of quantum operators. So here, not only x, so t, but also the entire thing is an argument of a quantum field here. Good. So then, given a eigenstate of x operator and the p operator, we say that this overlap between two eigenfunction or eigenvector of two operator satisfies this conjugation relation. Okay. So here we can do the same thing. So given a quantum field operator x, and then I can talk about the eigenvalue, and then there's eigenvector, there's eigenvalue. So the way you can think about this is that this is an operator, right? In my Hilbert space. So I can certainly find an eigenvector of that, and then eigenvalue will give you a configuration in space and time. Okay. Likewise, I can talk about this too. Okay, just like this set, x and p satisfy this relation. Here too, you can satisfy this. You can show that this satisfies e to the minus I now for integral, and then this. And I already stressed that this is good exercise. In order to derive this, all you need to know is that they are eigenvectors of this, which satisfy this. So this is only required information for you to be able to show that this is true. Okay, therefore, since phi and pi satisfy the exact same relation, you should be able to show that this is. Okay? Check.
Yeah, I have one question.
Yes.
So when we do the quantum mechanics, we have just as you said related time.
Yes.
But in here, the x and here both arguments. So then how should I take that?
Good, we're gonna do that too. So we're gonna, yes. So I will answer that. If not, ask me again, okay? All right, good. And then here too, in quantum mechanics side, obviously, one has to use this orthogonality condition to derive a path integral. And then this, you can write it as delta function can be written as this relation. I mean, this is not new because now you just literally insert here momentum minus, right? E. And then you just use this fact to derive this. Here too, in quantum field theory side, you should be able to show the same thing. So phi prime phi, you can insert this. And then using the fact that this satisfies this conjugate relation, we immediately get the analogous formula. Minus I, or sorry, I lied to you one thing. This should be 3 integral over vectors. This is a whole vector. You can ask, oh, well, why this is the case? Remember, I'm doing the quantum field theory in a canonical quantization picture, right? In a canonical quantization picture, what you do is that there is a time, and then you pick a time slice, which only have a space labeling, and then there I define the operators, and then I'm doing all these calculations. Okay, so this is a 3 integral. So likewise here, it is a 3 integral, and then basically the same thing. I of x by the same thing. So once you do understand that, then we can basically work out this without actually doing all the computations. Okay, so to do that, one thing that is useful is that let's actually write down the Hamiltonian. So Hamiltonian is what? Square. And then there's a spatial part. So let's write this as I. And then there's a spatial part. And then mass. And possibly B, if I roll. So from now on, I'm just gonna rewrite this entire thing as opposed to the pi part. The entire thing I just call it potential, only the potential of phi. Okay, but then this looks like, I mean, basically the same structure as the system that we studied. Previously in quantum mechanics, we studied p squared over 2m. So now mass is just 1, and then some potential. That's what we studied, right? So in this system, particular quantum computer system is basically identical to this system, except the fact that mass is 1. And then instead of dealing with a single position x in the time, we're talking about full space and time. So that's the difference. But anyway, let's do it here. Okay. So here in quantum field theory, we want to ask vacuum to vacuum transition. For now, let me pretend that I'm dealing with the free theory. So for now, if you want, you can think that this is 0. So I'm saying that because I'm going to use notation 0 as opposed to omega. So we talked about perhaps last semester that if I'm talking about the vacuum of a free theory, I'm going to use 0. If I have to talk about the vacuum of interaction quantum field theory, we're going to use this omega. Okay. So basically the question I'm asking is, we start with a vacuum at Ti, and then there's a time evolution between, and then I'm asking, what is the probability to land on the vacuum again, okay, in the far future? That's the question. Good. So this notation, if you want, schematically, what I mean, schematically here, vacuum, then I'm going to evolve by Hamiltonian this. Okay, so this you can have in mind if that helps for you. So then again, I'm going to insert. So now this Hamiltonian is functional made of the pi and phi, which are quantum field. So I'm going to insert complete set of a phi. So if I do that, I'm going to get integral over this phi n of x. And then, in principle, there should be time labeling. So here 2, x1, xn, and there's the time labeling. Just like quantum mechanics, I'm slicing it, and then I'm inserting all possible configurations at that time slice. Is that clear? Okay. So then there's a vacuum. Okay. And then e to the minus I Hamiltonian. Delta t phi n, then keep going until same. Okay. So picture the same again. So at each time slice, so I pick one time slice, then on that space, if you want, we can define another space, and then I can have a complete set of a eigenvector for quantum field pi n, and likewise for the pi n. Okay, so I'm inserting completeness relation for pi. That's what I'm doing. Good. So just like what we did, therefore this has a whole set of objects that looks like this. So basically, what we have to do, therefore, is we have to evaluate again this object. And guess what? If you do it, you will get something like, just like a quantum mechanics, line by line, basically it's the same structure. In this case, the reason why, in addition to just the dt part that we saw in the quantum mechanics, the reason why we have a d3x integral is because in this overlap expression we have d3x. Okay, So that's why there it appears this extra integration compared to a quantum case. So if you plug in all those factors, so then this will become n hat this. I don't know if you're interested in the expression for this, but anyway, for now that's not important. So it will give you by 1, by 10, and then basically sum of all this. So there will be right. Let me just say L sub n to say that this is line 5. So therefore, this turns into all possible field configurations, and then this is finished. Okay. So this is mu toy that is given to us. So we're gonna play with this method now. Any questions before I start playing with this?
그러면 저 파이의 파시브랑 컨피그레이션에서 모든 타임에 대한 컨피그레이션이 아니라 저 TI, TF 사이의 타임에 대한 컨피그레이션만 보는 거예요.
So I don't know. The question was when I do integration over a particular by n, were you asking this is configuration at fixed time n? If that was the question, the answer is yes.
그래서 저 액션도 그 타임 인티그랄이 마이너스 인피니티보다 인피니티가 아니라 인터널.
Good. Oh, good. So indeed, that was immediately what I was gonna say. So for this particular expression, there, since I was asking transition from ti, like definite time ti to the another definite time tf. If I do all this, obviously, when I have a sum over time, right? This is only action. Therefore, the question was. So for the t part, it was from ti to tf. Okay. And then there was this. So in this particular question, for this particular question with a definite initial and final time, this path integral comes with action where at least the time part of the integration is only from ti to t. Okay. And so later on, we will have to talk about for S matrix. So therefore, we're gonna send everything to the symptotic state, right? So there, we're gonna consider things goes to minus infinity for initial time, then plus infinity for the final time. Then action now in this path integral, action become full space and time integral. So this is good. So this is already useful. So let me say already why this is called a path integral quantization. Yes.
I have a very quick question. So in if calculation, we didn't use the property of ground state zero. So
Did not use the property of ground state 0.
so in your final equation, I think
Yeah.
there are no information about the initial state of at the initial. We want to calculate the overlap between the two ground states.
Yeah.
Two vectors. So
Yeah.
where can I find the information?
So yes, good. So you can see how that happened by looking at the first and last.
Yes.
Good. So one of the property, if you will, so this part is clear if you want. So let's just look at 5, 1, but let me just write this. And then to say that this has a structure that, well, this, okay. Let me drop all the integrals and stuff because this is too complicated expressions. Let me just write in a very schematic way. Pi squared over 2 with b, right? And then delta t. The integral is also here. And then obviously we have inserted the pi integral. And I'm using very schematic, that is not to replace the insert. It's okay, but let me insert a different part. E to the minus pi squared over 2 plus b pi. Okay. So this is this we know. So right, so this is eigenvalue, this is eigenvalue. That's how everything is done. Good. So then, in principle, we will be left with this piece for the first lines and then another piece from the last piece. Okay. So if you then keep track of everything, so let's just use this space. So then, good. So then this piece, you do then this integral to get Lagrangian, right? So you finished out the pi integral to get a Lagrangian. However, there's a subtlety. The subtlety could be that when we have not this piece, if we have this piece, that the difference compared to this one was that we had this and then the other with the phi, and then the phi combined to become kinetic. Okay. So here, in a sense, you're missing one piece compared to that. Okay. So one way to deal with this is you can either start from the phi, both from the initial and final, and then you can send to the vacuum by taking some limit. That's one way of dealing with it. Okay. Another way of thinking, okay, so that's one certainly working way of doing with it. So in other words, you start with the similar expression as in quantum mechanics, and then take some limit to send to the vacuum. That's possible. It's called the vacuum saturation trick. It's possible. But since here we haven't discussed that trick, let's just stick to this and then ask, what does this mean?
Yes.
Okay. Good. So in this case, let's see. So in this case, we are certainly missing one of the just bits compared to the other intermediate slides. So okay. So here we get, what do we get? E to the minus I d3 x pi x pi x. So super naively, let's ask whether vacuum. So vacuum is not an eigenstate of phi, I guess, because we know that if I have a vacuum, I can create a particle state. So vacuum naively is not a excuse me a eigenstate because if you were an eigenstate, then this will be 0. So this is not 0. Other than vacuum saturation trait, let me think how to answer that question. That's same as asking this question. Because if I insert another phi state, that's same as asking either what is this state or what is this not.
Yes. Also, I think my question is related with the, if we want, we can calculate the overlap between the two vacuum.
Yeah.
Or if we want, we can calculate the two arbitrary two state of phi.
Right.
So I think in this formula we can calculate the phi over phi.
Yes.
maybe it's impossible. So,
Yeah, that will give you literally line by line identical to the quantum mechanics derivation.
yes.
Yes, so that's possible. And then I was trying to say, therefore, once you calculate that, then you can take limit to extract the vacuum to vacuum. That's what I was trying to say before. But then that's certainly a working path. But I'm still curious how to understand that just within this calculation. So let's see. So basically, the question is, what is this? If this is 0, everything breaks down. I mean, breaks down in the sense that this is 0. Modular infinite prefactor.
But wasn't it be cancelled out by another vector for 1n? There should be another by n here.
You mean the similar factor from here, right?
Yes.
But this pi state has a labeling in it.
Oh,
Because, right? So this, I mean, starting here at time t1 slice, here I will have to insert at tn slice.
Oh.
So this pi, that might be actually possible. Okay, so let me, okay, good, that might be possible. So let's just stare at this again. And then we inserted a pi here, so we divide it as a pi1. And then, excuse me, here we're gonna insert pi n. And this is will not involve in the computation. The rest I can combine, right? Rest I can combine how I just shift the thing by 1, meaning so instead of previously we expect to see the pi, like this for j minus 1 there, right? Then, but if the first piece is this, I can combine this with the next one. So basically, you shift the by 1, the collecting process. Does that make sense? What I'm saying? Okay, so previously, so we were looking at this piece, c to the minus h delta t, okay, and then okay. So by doing this gave you like into the minus pi this, and the other one gave you plus pi j pi. So you combine these to say that there's a pi, and then like so, right? So that gives you sort of kinetic term eventually, kinetic looking term eventually, right? That's with the 1 dt you get actually pi time, and then looks like it was that term which you will have to do. Now what I'm saying is that if first state is the vacuum, you cannot combine like so, but then there's a next term here. And then you're going to have pi j plus 1, and so on the first. So you can combine with this, with the first term, but because second term you cannot combine. So you can still have a chain of a combining process. I'm guessing whether that will give you the rest. And then as Youngwoo was trying to say, yeah, because of delta function, this possibly can collapse with delta function with this. So basically you will end up with a 1 integral lab for pi, which will be identifying these two. And then that drops out, and then you just use the fact that vacuum is normalized. That would be 1. That's my guess, but let's check. Okay, I'll check and then answer that question whether that's what's happening or something else is happening.
하나 더 있어.
Sure.
그러면 저 백큐 말고는 그냥 QM에서는 이미 XI부터 XF를 다 그냥 계산할 수 있어요.
Yes.
여기서는 그러면 백큐 to 백큐 말고는 계산할 수 없는.
No, we should be able to calculate anything, but beauty is that, as I will demonstrate, not exactly this version, but a version which basically is a vacuum to vacuum transition amplitude with a little bit of extra structure, which I will explain basically today. That is enough to get the entire dynamic information. So in a sense, some sophisticated version of the vacuum-to-vacuum transition amplitude is enough, which includes entire dynamic information in it. So that's the sense we start focusing on the vacuum-to-vacuum. Yes, I mean, you might wonder, out of the world, why we are looking at vacuum-to-vacuum, which looks like least interesting thing to look at. If that was your intention of the question, the answer to that question is there is a certain version of vacuum-to-vacuum correlator which contain entire dynamics, which I will get to. Another question. Yes.
J랑 J 플러스 1번째 포지션이 될 수도 있고 프리드가 또 될 수도 있는데 그 델타 T 사이에 그 두 예를 들어 퀀텀 버전에서 XJ라는 포지션과 XJ 플러스 1이라는 포지션이 엄청나게 멀리 떨어져 있어도 사실 그게 다 인테그레이션 해버리는 거죠. 근데 문제가 안 생기나요? 예를 들어서 0초 때 여기 있다가 1초 때 안드로메다에 있다가 2초 때 다시 여기로 돌아오는 그런 경우도 그냥 패스 인테그랄에서는 고려가 돼버리는데
Yes.
근데 이제 성대론 쪽으로 근데 말이 안 되거든요.
네.
그런 거 어떻게 해결해야 되는 거죠?
Okay, so good. So let me see if I first understood your question. Let me rephrase it. You can let me know. So once we arrive at this formula, it says that if you're interested in some transition amplitude, what you have to do is that you have to sum over entire possible configuration weighted by the action with that configuration in it. And your question is, oh, looks like naively then we have to sum over all, not only reasonable configuration, but also totally crazy configuration, right? And for instance, this configuration does that include one like lumping here, but then 1 second after it's Andromeda, which is not causally connected and coming back? Should I include all those configurations? Okay, good. This formula at least says that yes, you have to include all possible configurations. But however, if the quantum physics, including special relativity, is designed properly, this will not include, I guess, configuration that explicitly violate causality, for instance. So I mean, if you were not this way, obviously, yeah, whatever, you go wild. You include every possible sum. But it is weighted by the action. And then one thing to be checked is that if you look at the configuration, which clearly violates some of the sacred principles, you should get like 0 weight. I mean, this will regulate to check whether you give me this, let me check. Okay, I give you 0 contribution. You give me some good one, let me check, and then I give you a proper good contribution. Okay, so this will control. This is the control power. And we will see some of those examples today too. I think in class. Okay, any other question? That's a good question. I mean, obviously, then.
제가 알기로는 그 퀀텀 메카닉스에서는 퀀텀 메카닉스에서 프로저비티가 그러니까 뭐라 그래야 돼? 프로저비티. 그러니까 예, 그 빛의 속도보다 빨리 정보가 전달되는 문제는 진짜 문제는 아니고 왜냐하면 퀀텀 메카닉스는 애초에 스페셜 렐러티비티에 고려한 띠어리가 아닌 경우를 상관없고 퀀텀 필드 띠어리에서는 저런 패스들을 고려하는 게 상관이 없는 이유가 제가 알기로는 그러니까 이제 여기서 그 안드로메다로 가는 어떤 패스가 나왔다고 했을 때 그거는 실제로는 진짜 이제 파티클이 여기 있다가 안드로메다로 간 게 아니라 안드로메다에서 어떤 파티클이 크리에이트 되고 여기서는 아닐레이트 되고 뭐 그런 개념으로 생각을 해야 된다라고 어디서 들었는데 그렇게 이해를 하면 좀 뭔가 다른 이 설명하신 거랑 좀 다른 것 같아요.
Good. So first let me check your question and then I can also answer. So in quantum mechanics, first you said that the reason why we don't have to deal with causality because naively quantum mechanics alone, we don't actually put it in the constraint from the causality. You can view that way too, but perhaps another way of viewing it, if you believe that quantum mechanical system we see in the lab is actually non-relativist limit of the fully relativistic quantum field theory, then that is like taking the speed of light to infinity. So basically collapsing like that. So therefore, you are collapsing out entire space-like separation. So by definition, any of your formulation does not include causality violating this. In that sense, you are guaranteed to satisfy causality. Okay, so that's another way of thinking about it. Going back to quantum field theory part, one thing that is important is that this is a classical configuration. This is not an operator. This is a function. Okay, you're summing over function. but when I say classical configuration, I don't mean that this is a configuration that satisfies classical equations of motion. All I mean was to say that this is a classical function as opposed to being an operator. And in fact, through the derivation, you saw what this is. This is eigenfunction of classical quantum field phi. Okay, so this is by no means just including a configuration that solves the equations of motion, but include all possible configuration that that operator can give you. And that also answers the question too, because I'm summing over. So what is the complete set of field that we can possibly expect to get? Well, by construction, we've been doing this, which means that the sum over phi, also related to that question, is over the sum that this quantum field that can give you, right? And then you can ask, okay, then can I possibly get a configuration which is explicitly violating some of the sacred principles, which you not if you, of course, dealing with a quantum field theory that, manifestly satisfying classical, causality or unitary and so on and so forth. So that's the sense I was trying to say, that we don't actually say technical work. This will regulate. If you try to sum over that thing, since it knows that that's not part of the universe space, it will not give you a contribution to this method. That's how I was trying to answer. If you still have a question, you can ask.
네, 괜찮습니다.
Okay, good. All right, so then let's move on. Okay, so quickly let's talk about the classical limit, and then we will develop a slightly more powerful formalism. So let's check whether this formalism gives us the correct answer for, say, let me just write the vacuum to vacuum transition amplitude, which is the sum over this. Okay. Now, in order to check the classical limit, we have to put it back. So now we have to reintroduce H bar. And H bar appears as like so. If you put it back H bar correctly. One quick check is that what is H bar? H bar dimension is the same as E times T, which is the dimension of action. So you have to divide by that. There's no dimension full quantity can appear in the exponent, right? Because if you tail expand, that means that you're summing over all possible terms with all different dimensions, which is easily defined. So it should be only dimensionless quantity sitting there, so it should appear like that. So then the classical limit, now we are prepared. The classical limit is by taking H bar goes to 0 then. So in this limit, for instance, X commutes with P, and so on and so forth. All sort of classical picture arises. So then this is like summing over something with a crazily oscillating phase. So I'm scanning over phi, and then this phase changes over that scanning region, but all of that is crazily oscillated. So a generic piece of a field space, therefore, will give a 0 contribution, because this is a wild phase oscillation and there's cancellation. Okay, technically you can invoke Riemann-Lebesgue theorem or lemma, whatever. Okay, if there's integration where infinitely oscillating phase that add up to 0. So therefore, you see that generic piece of the field space will make 0 contribution. So therefore, as we scan phi, so suppose I'm scanning over the phi region, in order to make a non-zero contribution, I don't want to see, so basically action should not change, right? Only then I will make a contribution which does not die out by wild phase oscillation. So therefore, in this limit, we see that phi such that this, in other words, phi is a stationary phase point that makes a contribution. So it works in a sense. If I take a classical limit according to one notion, meaning generic notion of quantum mechanics, I recover the fact that in that limit, obviously, I should only get the classical configuration according to quantum field theory notion. So it works. Okay, good. Now let's get some more useful facts about it. So now I want to show that this formalism will give us time order products. So ultimately, what I want to show is that ultimately the goal is to show that time order product of n operators, like so, that we're interested in, will be given by
Is I in the Heisenberg picture?
good. So yes. So here I am in Heisenberg. I was gonna say, clarify it later, but yes. So good. So therefore, two things that we want to see here. A path integral with some insertions of classical function will give you automatically quantum object with time ordering. So that's how we want to see first. Okay. And the generic time order endpoint function in interacting vector can be obtained by the path integral according to these formulas. And then we will understand the meaning of this expression in detail. That's the goal. Okay, so the first thing first. So in order to see that, the first thing we want to check is as follows. So let's look at a vacuum, and then let's just look at the insertion of a one operator at a particular position and time. So here I'm just putting J, but we don't have to in principle. You will see why I'm putting J, which will be just bookkeeping date for now. So if you follow the derivation then of the path integral that we have done, then what you get is the following. So there is a phi e to the minus h of t by n, and then you're going to have a lot of chain. But because there's an operator inserted at a particular time step, then what you have is phi j plus 1, then you're going to have minus h of t, and you will have this operator inserted like this one. Ij, and then keep going. In other words, compared to the previous derivation, one difference is that when you insert all of that at a correct point of the time, you also have to have this operator inserted, right? Because you're going to slice out, but at that particular time, obviously this will appear at the corresponding time. Okay, that's one difference that is made. Other than that, everything is the same. So then, since this is an operator and this just gives you a function, okay, and then this will come out of the integration, the rest is completely the same. So if you follow then the same step, you will eventually arrive at the point where it's a path integral, everything is the same, except the fact that there's a one extra classical function inserted. Okay, so that's therefore you should get this. So we see the relation between path integral with the one insertion of a classical function. It's same as asking now vacuum expectation value of an operator inserted. Okay, exactly the same token, then you can ask backward now. Now let's ask the following question. So now I'm going to look at the path integral with the two functions. X1, let me just write the four space and notation.
Professor,
Yes.
well, shouldn't that define just at the third line should be xj and tj because that is so that you are summing the entire possible, all possible insertions.
Sorry, I didn't catch the question. Can you say this?
So at the third line, we will get phi xp. I
Yes.
think that should be xj and tj.
Yeah, so good. So yeah, that's what. So this is done here. I'm summing of the entire x and t. Okay, so this is a particular time and space. But okay, when I say just t and x, I just mean particular time t and particular point x. Right? So I didn't have to put j here also, but the reason why I put the j there, A, I follow textbook, B, because then you know when to stop and put this operator. But once you know exact time, exact x, you know when this operator has to apply when you do the slicing, right? Because here, there's a time, and then suppose I inserted my operator here, but then as you do time slice, you know where to stop. At that point, this operator has to act on this slice, right? That's what this picture means.
Yeah.
Now let's look at this. Now we inserted a two phi in the path integral. Again, everything here is a commuting regular function and so on and so forth. Okay, other than the fact it's very hard to do the computation. Okay, now what is this? So now so now this should be, if you do the exact same thing, it should be insertions of x1, x2 operator. Okay, so this is a guess. And the answer is that no, it should be time ordered. One immediate way to see why this fails is that here they're totally commuting. This is the same as this, because this is classical function. But here, obviously, they don't commute generically. They do commute on a space-like separation, but when you want to ask the physical question where this is interesting, then they will be generically on the time-like separation. They don't commute. So obviously, this cannot be the same as this without a thing. But under the time ordering symbol, you know that they're going to commute. Okay, that's good check. That first of all, you will not be naive with this, something like time ordering, where operator commute. But obviously, you can just explicitly check that this is actually true. Why is that? So once you specify time t1, t2, right? Then when you do the slicing, obviously, if you inserted a phi1 here and phi2 here, it will appear according to the ordering of the time because you're slicing, right? So automatically, if you compute this times with the time ordering, right, then you explicitly know which ordering I have to do the computation. And it will appear according to the way, but although at the end of the calculation, it doesn't matter which order it appears, because the classical function doesn't matter. But the whole point here is that this matches on the time order, not the regular correlation. And you can explicitly derive. Okay, so then with that, I can write down a generalized version of that. So let's write 3. So this time ordering. So from now on, let me just simplify my notation. From now on, I'm just gonna call phi1 and phi2. Even dropping hat. Okay. So we understand whether we're talking about an operator or a function. So therefore, if we do the path integral with the insertion of n functions on the quantized side, this will give you a time order n function. Yes,
There should be the normalization in the denominator. Integral
here.
denominator in the right side of the d.
You mean this?
Yes.
Okay. So far, I put n. Yes. Good. So I will discuss that basically now. Okay. Good. So probably it is useful to mention that therefore path integral sorry, capacitive vacuum to vacuum transition amplitude that we talked about, you can think of it as a partition function. Okay, so in the statistical mechanics, right? For instance, we have sum over eigenstate into the beta Em. If we talk about the simple one, this is the partition function. And then you can compute the expectation value of O by doing something like, eigenvalue, let me put like so, weighted by this factor, and then you divide it by this because that's the normalization factor. Okay, so basically, and that's what probably you mentioned normalization factor, but we'll see that immediately, that this is not an analogy, this is actually solid correspondence. This is a solid relation. In fact, taking given a quantum field theory in the Minkowski signature, you can pass on to Euclidean according to the analytic continuation we talked about. You'll actually get exactly the picture of this sort. Okay, not only even it's similar, but it's actually exactly the same. Okay, good. So again, I want to get this point. So let's do it. Good. So far, I was imagining sort of a free theory. So I'm using this notation. And then now we are interested in interacting quantum field theory. So you can ask yourself, if it is interacting quantum field theory, so here, let me keep this expression, for a interacting field that we talked about so far, Yukawa or gauge interaction and so on. So first, generically, what you have to do is that you have to first pass from the Lagrangian to Hamiltonian, and then we have seen that sometimes there's a subtlety if there is a constraint. But then, even if you manage to do so, then you have to derive. But then the derivation gets more complicated because if you were free, then there's a Gaussian integral that you have to do, right? So what I'm saying is that if you're talking about free theory, then the sort of integration you have to do by j plus the e to the minus h delta t. So this can be done by only Gaussian integral that we talked about. But for interacting QFT, then if you want to look at this, then Hamiltonian in principle can have a parameters expressions, right? Like phi q, phi 4, and so on and so forth. So immediately, it's not clear that whether Gaussian integral will get you the final answer. And generically, it doesn't. So it's hard to get explicit derivation of path integral if you want to do it for generic interacting QFT. Okay? So then what do we do? In that case, so for interacting QFT, therefore, we can take, for instance, now I'm talking about interacting vacuum. So we're gonna now take a leap, saying that we're gonna take this as my now definition of a quantum field theory with interaction in it. Okay, so what is justification? Well, justification is through the now computations and seeing the formulas that we saw from a canonical quantization, but we can rederive from this quantization. Okay, so we'll see immediately a couple of few key examples. Question. Okay, now let's check the time. I want to go a little bit further, but let me check with you. Okay. Sorry, wait. Okay, so we said that we're gonna have a couple of makeups in the breakout way. Okay, and who has a time limit after the class? We are already in the after the class now. But I'm asking still. Okay, so since we missed one class during KPS meeting week, we will need at least 3 extra sessions, like half an hour extras. Okay, so is today good to finish a little bit more about this, or you feel like that is like, okay, good, let's go. So we will go up until like 4:30 or around that time, just like 20 more minutes. Okay, good, because I don't think I have hit the punchline yet, so let's go a little bit. So good. So what I said here is that for like free theory, we have actually have an explicit derivation, and for interacting theory, generically it's very hard to actually derive explicitly. We're gonna take this as a definition and check. Let's check whether this is a good definition or not. Good. So then. Yes.
영이 인터랙팅 백킹이었고,
No, this is my interacting vacuum. I don't know if I put it in notation. This is my interacting vacuum.
그럼 아까 계산한 건 0, 0이.
Sorry?
아까 계산한 건 0, 0이. 0 주요.
Yeah, so the thing that I computed before was 0, 0. And then remember, I only used the free action, quadratic action. Like that. Okay? Good. Okay. Okay, so then from this starting point, we can state a couple of things. Good. So then first thing I want to say, this is good, and this generically include a quadratic piece or free piece, and then now this would have some interacting part of the action, like so. So in this definition, then we want to get time ordered. Well, there was notion that there's a Hamiltonian picture. And with the normalization of interacting vacuum transition amplitude. Row, I1, again, I action. So we get this. So what is the logic here? The logic was this. So previously, with the free theory, when I have on the quadratic action, we saw that with this now free vacuum, this was the same as that. So we saw that, or we argued that at least. In other words, one can derive that. Okay, so let me say that again. When we are dealing with only free action, then this equality where now interacting vacuum is replaced by the free vacuum, that can be established. So if we do the path integral with insertion of n function, that gives us quantum mechanical vacuum expectation value with a time ordering. So that we talked about. Okay, and now if I take this as our definition, even in the presence of interaction, the time ordering part doesn't change. So it will pass through. But the only thing that is subtle here is that since I have not picked a normalization for the vacuum to vacuum transition amplitude, I will have to have the generically this. Okay, so that case will give you that, but I just normalize by this. So I'm literally writing up and down. I have not done anything different, but I just divided by this piece as it is. Okay, good. So then one can actually normalize. Here we can choose normalization. Like so. Okay, so then on the left hand side, then it becomes just that. So then on the left hand side, we have just, let me drop each part. This is left hand side. But then the right hand side, this gives us the fact that the vacuum to vacuum is this. So that means this is 1. That means formally I'm taking n to be inverse. So since the first I picked this to be 1, that's just 1. But again, n is anyway inverse of this. So this will give me which obviously is considered as if I just cancel out n factor and then for that. But you can do into 2 different ways. Okay. So this is basically their notion of a path integral so far. Now we will actually introduce and develop a machinery to, because there was a question before, why in quantum field theory you look at this back to the vacuum, which looked at least interesting, but I'd say that it included all possible dynamic information. If you look at the slightly more sophisticated vacuum to vacuum traditional. So that's what I want to introduce now. But are there any questions so far? Yes.
It's upper and lower and are all the same.
Good. So the question was, yes, I think so. Because if you think about it, where this appears is that starting from the initial and final state. So the question is whether these two are same. Let me answer that. So the final state and initial state, right? And then let me just put like so. There's an x slice you put it in, right? And then you want it to compute with the Hamiltonian evolution. And then you put a lot of x's. Then whether or not you have extra operators, basically you have extra insertions of operator here and there. Okay? But then you also put key slices, right? To be able to compute this. And then all this does is that you're acting on the, eigenvector, and then you pull out the function. So extra insertion cells basically give you extra functions. And then the rest, which comes from basically collapse, overlap of P with the X and then P with the X. That is universal piece. And then it is that Gaussian integral, for instance, gave you this n factor. So that is universal. Either you have this or you can ask in non-perturbative definition of quantum field theory, whether you cannot derive this expression for interacting quantum field theory, whether this is universally same or not. Yeah, in that case, well, in that case, since I don't know the nature of this, right? But good. But then at least one can argue as follows. So now this is not a quadratic. So it's not going to be just Gaussian integral. It can be more horrendous integral. But suppose you're totally powerful and you can actually do integration nevertheless. Then the structure is basically still the same. Right? There's insertion style operator, and then it gives you a function after acting on the eigenvector. Then you're left with the same set of integration, which is identical to only the vacuum-to-vacuum integration. So in that sense, I would argue that this is still the same. Okay, any other question? Good. So, good. Now I want to introduce what's known as a generating functional, but hopefully this expression makes it totally clear why this is called the path integral quantization. Okay, you do the totally classical computation, and then you get quantum mechanical expectation value. So now let's introduce what's known as one of the first generating functional. So I'm not sure if we're going to have time to talk about the rest, but at least let's talk about the first generating functional. So here I will introduce the object known as J of source. Let me write down the expression and then explain the physical meaning of that. So this much we have seen with n in front. That was a vacuum to vacuum transition, right? So that times some n was a vacuum to vacuum. So first of all, I picked n to be 1 because at the end of the day, they cancel out. So it looks like it is this object that matters in the computation of a time order correlation function. We pick the 1. B, this here, J function is a classical source. And we already talked about classical source before when we talked about, for instance, field. So if we say, oh, let's talk photon field to some classical source J mu. And then what those source does is that given a source which may be supported in some compact support of space and time, there's J, where this is the region where J of X is non-zero, and they can basically shoot out or generate this particle excitation phi of X if you want. Okay, eventually it will work like that. And then we also talked about particular source before. For instance, if I was talking about photon field, and then if this were vector current source, then we will talk about actual dynamical source that can actually produce this, right? So microscopically, it might be some chip with also kind of quantum mechanical quantum QED processes that's shooting out the photon beam, laser beam. For now, we are modeling whatever that happens inside of this box. I'm just going to model that with classical function for the source. Okay, so why this object is useful? This is powerful. So first of all, let's know the following. So first, if I consider z of 0, with the source being 0 turned off, this is basically vacuum to vacuum transition up to this n factor. So divided by n. So I'm just using this. Okay, so make sure you go. So therefore, you might say that this is actually vacuum transition in the presence of source divided by n. So I'm almost attempting to drop n, but just so that you don't get confused with the factors of n there, I'm just putting in like putting them in exclusively. So J, physically, you can first say, this is a mathematical expression. First of all, you can say that it is a vacuum to vacuum transition in the presence of source. So now I'm going to demonstrate what is actually the difference between these two. Okay, and therefore demonstrate that this guy will have all possible dynamical information in it, and then I will make sharp by actually writing down a more mathematical expression. Okay, good. So let's first talk about this J of 0, which is just the vacuum to vacuum transition with the source being 0. Okay, modulo n factor. So what is the picture here? So let's take the time. This is my time axis. And then I'm going to look at time goes to plus infinity. I want to see that it is a vacuum state. So that's the final vacuum state. Then I also want to look at t goes to minus infinity. And then it's far past. I also want to see vacuum. Good. Now, so in that case, you start out with a vacuum, right? And then you want to end with a vacuum. And then the question is physically, in some interacting quantum field theory. So let's talk about the scalar field that can possibly has a cubic interaction, quartic interaction, and so forth. Okay? We can ask, what can possibly happen? One possibility is you start with the vacuum, nothing happened, and end with the vacuum. An infinite amount of time. Another possibility is that at some point, at one point in the space and time, two particles pops out, and then they annihilate back. That can happen, so you can still go back to vacuum. Or we can start talking about slightly fancier one. Okay, so I start over here, and then maybe I can have a loop in the middle. Or I can have a lot of loop processes happening, right? And all sorts of these things you can have. Whatever. If there was a cubic, you can also do this. All kind of thing happen. Well, you can end with the vacuum. So all this class of diagrams that I draw doesn't have external length, right? But it just have loops. They're called the vacuum bubble diagram. So you learn that therefore vacuum to vacuum transition amplitude in the absence of the source is basically sum over entire possible vacuum bubble diagrams that is provided by the theory, given once you specify interaction. Okay, that's what we have. Now let's ask, what about this now? We're going to ask again the vacuum to vacuum, but in the presence of source. Now let's ask what happens. So I'm going to draw a similar diagram here, which is now vacuum to vacuum in the presence of source. Let's see. So this is I. I need a more space here. So here again, I want to end with vacuum in the for future. Then the far past, I want to start with the vacuum. Again, you can have all this kind of beautiful bolts. I like bolts. Okay. So they should be there because it satisfies this criteria physically. But what can also happen is that, oh, at some point I have a J which is non-zero and shoot out and then end with J. Still, I start with the vacuum, end with the vacuum, but intermediate time something happened. And I can get fancier. So I can go like so still, but I can dress with some more close and sort of others. It is possible. So J goes to J. We can say, why not just the multiple J's? Yes, sure. So now I can turn on two J's, then they can go. Good. Then they can end with J. Okay? And a lot of diagrams that I don't specify, you can have 2J come out. And depending on the interaction that you specify, you can have a lot of them. And why not just 4Js? You can have many multiple J diagrams. Example. They all are included in this simple project. So you see hopefully that I am organizing according to order. So this is J to the 0th order diagram. Okay? Because there's no J. So you only have a bubbles. And this class diagram, for instance, corresponds to J square diagram. Okay? The two sources. Either this, I'm saying this is a sum. I'm not saying they're product. Sum. Okay? And then you can have J to the world and then many JNs. So you see now clearly that this single object effectively includes all possible, if you get rid of this JLAX dynamical object. This is what you want to see. This is an endpoint correlation function, and from this you can extract asymmetries by taking LSD reductions. So this object includes all of that. Hopefully this discussion makes clear that you should expect this is the case. Now let's make it sharper. How we see that this is indeed the case for this single object. Questions?
Then what about, you only talk about J
J-even?
Yeah.
Oh, no, you can talk about J-out. Oh, sorry, yeah, am I? Yes,
So yeah, this is all out.
Yeah, any n,
Yeah, thank you.
any n. Unless theory has a secret discrete symmetry that disallow other n. You might ask, oh, how would J know? J sounds like classical source. How would J know that theory has that certain symmetry? In fact, one best way of studying the symmetry of theory is by studying properties of J. And it all captures the entire symmetry. Okay, good.
Oh, then J to the first order is okay.
Good. So yeah, that is in principle okay. That's a 1-point function. Right? So if you only had a J to the first, so that will look like this shooting up one guy. Oh, you're asking in the vacuum to vacuum transition. Oh no. 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 But such an object is meaningful. I guess that's what I was trying to say. Because you have to go back. Oh. No, actually possible, depending on theory. So I have to specify. So for instance, if you had a cubic, you can just go around. You can end with that. So it all depends on the particular interaction, but if you do have this, then it. Okay, good. So now let's make this statement sharper, actually, formally. So J of 0, J, sorry, let me write. Integral action. Okay, so I'm gonna play in two different ways this expression. Okay, so the first way, I'm gonna play like this. So first, I will do this. What do I want to do? So this is the same as everything is classical. This is such a trivial expression. But depending on how you do this expression, you may do different. So this is a particular instance of, for instance, like some instructional classical function, as we call it. In other words, I guess what I want to say here is that this. So therefore, J Z of J divided by Z of 0 is same as this. Well, you might say, you may laugh, but this is the difference with respect to full action. Okay, full action, which means that I'm talking about full interacting vacuum. Sorry. And then I'm going to divide this according to that definition into the as full action. So this, if you want in previous discussion, if you want, you can put it back n factor, whatever relative n factor. Then this is the same as vacuum expectation value of time ordered expansion of either time source. Divided by this. So now this is an operator equation, and here the only operator is this phi. But crucially, J is still a classical function. Okay. Now, clearly, if you have this expression, you must have a temptation to do a Taylor expression, which you do. So let's do it. Therefore, that can be written as some. Okay. Hopefully that is enough space. Let's do it. And so I'm gonna do Taylor expansion. Or n factorial. And then e for x1 to e for xn. Then I'm gonna have by 1 by n. That's new. So I'm expanding this by yes.
There should be J.
J, where are my J's? Yes, exactly. J1, Jn. Yes, that's crucial. Thanks. It's crucial. Because I'm doing the Taylor expansion in J. Now, hopefully that's clear. Okay? So then this, good. So then this becomes, sorry, let me check one thing. It's all about the M. It's all about the normalization. Let me make sure. Yes, no, everything is fine. Although, okay, the reason why I stopped here is that this was this, and then we say that I can already choose a normalization where this is 1. And that was the same as dropping this M, if you remember. Okay, so therefore, let me take a normalization where this is 1. So then you see this captures the basically point that I wanted to say. So, yes.
Little bit minor point there. There should be I.
I is crucial. Where is one? Yes, every J has to have I. Excellent. Good. So then, what is the punchline here? The punchline is that Z of J divided by Z of 0 is a basically formal Taylor sum, Taylor expansion in powers of J, and then the coefficient is beautifully time ordered endpoint function in full interaction. So that matches to this expectation based on picture, right? I was looking at the vacuum in the presence of J, it was this. Okay, and then the point here is that yes, I can have all possible endpoint function in time order sense. And then all of this diagram can be multiplied with this any of these vacuum bubbles. So when I say I divide by Z over 0, I basically mod out all these unnecessary vacuum bubbles and only looking at this species without a product with the vacuum bubble diagram. Okay, so that's what this formal expression is all about. So indeed, this is super powerful, and that's why you can see that this is a generating function. Because if you know how to compute this single object, this generating functional, you can now simply learn how to extract a endpoint function, which the answer is you just need to do the formal functional derivative. Okay, so let's establish that and then we'll end. So how do I extract this coefficient? So that is this. So given this, where is it? Yeah, given this definition, you see that if you take J, and then if you do the functional derivative with respect to J of X with the minus I, because to compensate that plus I, acting on J, what do you get? So this is, let's just do it. This, and then if you do it, you get phi of X. So in other words, let me do what you want. If you're confused. If I want to do this functional derivative of this, then I use the fact that if I had J of X, J of Y, this is 4 delta function. Okay. So then you're pulling out this vector, and then you're back to the cell action plus J dot Y. So So from that, it's clear that therefore, if I have done functional derivative with respect to j of x minus I, acting on j of j, and then set j to 0 at the end, you get this, right? So I set j equal to 0 at the end, you get this. Now, in order to get the correct, vacuum expectation value, you need to normalize by this factor. So that is nothing but 1 over z over 0. So this we learn from that. This is full vacuum expectation value of 1.0. You put time ordering if you want, but the single time. An immediate generalization of that thing is 1 over z of 0, which will give you this normalization factor. And then you can take any derivative acting on this generating function, but at the end, you set source to 0 so that you pull out a whole bunch of factors, as much as you need. At the end of the day, you get rid of this source term and then normalize it. So that will give you okay? And obviously, that is totally consistent with the definition of Taylor expansion, right? So Taylor expansion, nth order, 1 over n factorial, and derivative of j, and then you just write down powers of that, right? So therefore, that is the coefficient. So, good. So this is how you can compute or generate all kind of this thing. Once you know how to compute j, and indeed, in a Euclidean signature, this will be exactly a partition function of a statistical mechanical sense. Okay, any other questions? Probably I should stop here. And then I'll talk about next time. I'll start with the second way of playing with this expression, reproducing one of the formula that we derived last semester from current quantification. Any question? Okay, I'll stop here.